Hi everyone, in today's video we are going to be deriving the heat exchange rate for co-current and countercurrent heat exchangers and express this in terms of log mean temperature differences. So to first start out, I want to explain what a heat exchanger is. So a heat exchanger transfers thermal energy from one fluid to another without them directly mixing. And based on the setup of this, it can either cool something down or heat something up. So for this example, I want us to imagine that we have one tube inside of another. So we're going to have this large tube on the outside and a smaller tube on the inside. And we're going to say that we have a cold stream of fluid flowing around this inner tube and a hot stream flowing inside this inner tube. And of course, there's going to be heat transfer from this hot fluid to this cold fluid. And so co-current means that both of these hot and cold streams are moving in the same direction, whereas countercurrent means that these streams are flowing in opposite directions. So we can actually write out an expression for this. So our expression is going to be that our heat, or Q, is going to be equal to both convective and conductive heat transfer. And so to represent those all together, we're going to use the variable U, which is our overall heat transfer coefficient. This is going to be multiplied by our temperature difference from this hot stream to this cold stream. And then we are going to be taking this difference, this heat transfer over a certain cross-sectional area. So we're going to have to multiply by dA. And now normally if you saw this, maybe your first instinct would be to go ahead and integrate this. But the issue here is that we have these temperatures that really aren't in terms of our area, so we wouldn't be able to integrate that. And so what we're going to do is we are going to take the mass flow rate of our hot stream and multiply that by the heat capacity of our hot stream. We're also going to take the mass flow rate of our cold stream and multiply that by the heat capacity of our cold stream. And so what those get you are the mass flow rate heat capacities. So this will be the mass flow rate heat capacity of our hot stream and the mass flow rate heat capacity of our cold stream. And that way we can start to figure out things to be in terms of area to ultimately take an integral later on here. And so we can actually relate this to something that we have learned pretty early on in general chemistry. If you remember that Q, or heat transfer, is equal to MCAT, our mass times our heat capacity times our change in temperature. So if we remember that equation, then we can kind of put our two equations up here that we just made in terms of that. So that is going to be that the derivative of our heat flow is equal to, if we start off with our hot stream, that is going to be the mass flow rate of our hot stream multiplied by the heat capacity of our hot stream times this change in temperature dt. And now what we said was that our mass flow rate multiplied by that heat capacity is equal to the mass flow rate heat capacity. So we can change this to be the derivative of our heat flow is equal to the mass flow rate heat capacity of our hot stream multiplied by the change in temperature of our hot stream. And this is going to be negative because if you think about it, if that heat transfer is occurring from this hot to this cold stream, then the temperature of our cold stream is going to be decreasing. Whereas if we think about the cold stream here, it's going to be the same setup, except it is not negative because we are increasing let me make this more clear. We are going to be increasing that temperature from our hot to our cold stream. And so we can kind of make this over here into that same Q equals MCAT equation. So this is going to be the derivative of our heat flow is equal to our overall heat transfer coefficient multiplied by our change in temperature, and then still multiplied by that derivative of our area, the cross-sectional area that we're working with over which heat transfer is occurring. And if we want to start thinking about what causes this heat transfer, like what is our driving force here? The driving force here is going to be this change in temperature. That change in temperature is driving this heat transfer. So like I said, our driving force is going to be this change in temperature, and that is equal to, of course, our hot temperature minus our cold temperature of those different hot and cold streams. And so if we plug in our values that we found over here, if we solve for those, we can plug those back into here. So this is going to be the derivative of our change in temperature is equal to negative the derivative of our heat flow over that mass flow rate heat capacity of our hot stream minus the derivative of our heat flow divided by the mass flow rate of our cold stream. Now, if we separate this out, we're going to have the derivative of our change in temperature or driving force is equal to negative the derivative of our heat flow or our heat transfer multiplied by -1 over the mass flow rate heat capacity of our hot stream, because like I said, this has to be negative because we're going from a higher temperature to a lower temperature, minus 1 over the mass flow rate heat capacity of our cold stream. So now we can plug in for the derivative of our heat flow or our heat transfer. So we're going to have the derivative of our driving force, our change in temperature, is equal to negative the overall heat transfer coefficient U multiplied by our change in temperature multiplied by our cross-sectional area. And then, of course, we have the rest of our equation. Just plug that in quick. We have our mass flow rate heat capacities. So now what we can do is move our delta T term to the other side and integrate. So we're going to have 1 over delta T. The derivative of our change in temperature is equal to the negative overall heat transfer coefficient multiplied by our derivative of our cross-sectional area. Then we're going to have -1 over the mass flow rate heat capacity of our hot stream minus 1 over the mass flow rate heat capacity of our cold stream. So now what we can do is integrate. I'm going to move this term over here and move this over. All right, so now what we can do is integrate on both sides. So let's think about what this delta T actually means. And so we're going to have inlet temperatures here at position 1 and outlet temperatures here at position 2. So if we integrate this, this becomes the natural log of our change in temperature at position 2 divided by this change in temperature at position 1. And this is going to be equal to, we can take this term out of our integral because those are not dependent on our area. So this is going to be equal to negative u times, if we do the integral of dA, that becomes just our area term. So negative the heat transfer, overall heat transfer coefficient multiplied by the area, multiplied by our terms here for our mass flow rate heat capacities. So now what I want to do is start talking about these terms over here and plugging in our values for those based on what we said about our inlet temperatures and outlet temperatures. And so if we plug that in, this is going to be equal to the negative mass flow rate heat capacity of our hot stream, and then this delta, or this derivative of our hot temperature, that's going to be the hot temperature at position 2 minus the hot stream temperature at position 1, or whatever's going in. And then if we do the same for our cold stream, this is going to be the mass flow rate heat capacity of our cold stream multiplied by, this time, the temperature of our cold stream going in minus the temperature of our cold stream leaving, because the temperature of our cold stream leaving is higher than that of the temperature of the cold stream entering. So now what we can do is we can take our equation that we just found and plug in our numbers up here. So what we're going to have is the natural log of delta T2, our temperatures leaving, over delta T1, our temperatures, or sorry, yeah, our outlet and inlet temperatures. This is equal to negative U, our overall heat transfer coefficient, multiplied by our area. Now we can plug in our values for our mass flow rate heat capacities. So if we do that, this is going to be multiplied by our temperature of a hot stream leaving minus the temperature of a hot stream entering, or at position 1, divided by Q minus our temperature of our cold stream at position 1 minus the temperature of our cold stream at position 2, divided by Q again. Now, if we take Q out of our equation, what we're going to be left with is the natural log of the change in temperatures at position 2 divided by the change in temperatures at position 1, equal to negative U, our overall heat transfer coefficient, multiplied by the area, multiplied by 1 over Q, multiplied by the change in temperature at position 2 minus the change in temperature at position 1, so delta T2 minus delta T1. And now if we want to solve for Q, Q is going to be equal to negative our overall heat transfer coefficient multiplied by our area, multiplied by delta T2 minus delta T1, divided by the natural log of delta T2 divided by delta T1. And this term right here is our log mean temperature differences. So that's that log mean temperature differences is that term right there. So now when we're thinking about co-current and countercurrent heat exchangers, for co-current, eventually you're going to reach a point where your hot temperature and your cold temperatures are so close together that that delta T is going to be effectively zero. Whereas if you're looking at your countercurrent heat exchangers, there that gap is only going to widen. So you're going to have a larger amount of heat transfer over time in relation to co-current, which is why countercurrent may be preferred as you're getting more heat transfer over time, whereas co-current, that delta T or that change in temperature slowly decreases and they eventually meet each other and it's that difference in temperature is effectively zero. Okay, so now what we're going to do is we are going to explain the concept of heat exchanger effectiveness and how it can be used in conjunction with NTU and Cmin divided by Cmax ratio for sizing heat exchangers. So when we think about the effectiveness or the efficiency of a heat exchanger, that is going to be our heat transfer Q over our max heat transfer, Qmax. And one thing I forgot to mention before that I'd like to bring up now is the importance of how fast our fluid is flowing. So that flow rate is very important. If you had, let's say your cold stream was flowing very slowly while your hot stream was flowing very quickly, you're going to have a greater heat transfer from that hot stream to that cold stream and vice versa. So now if we want to talk about cooling a hot stream, this relationship is going to look like the mass flow rate heat capacity of our hot stream multiplied by that hot temperature going in, so the inlet temperature of our hot stream minus the temperature of our hot stream leaving. And this is going to be divided by the minimum mass flow rate heat capacity. And that could be from either your hot or your cold stream, whichever is flowing slower, because that's going to have that greater difference in temperature and that greater amount of heat transfer. And so this is going to be multiplied by the temperature of your hot stream going in minus the temperature of your cold stream going in, because that's your greatest difference in your temperature right there. And so this value right here on the denominator, that is going to be your max heat transfer or that Qmax. Now, if we want to look at heating up a cold stream, it's kind of going to be the same principle here. You're going to have your mass flow rate heat capacity of your cold stream multiplied by the temperature of your cold stream going in minus the temperature of your cold stream going out. Once again, this is going to be divided by that minimum mass flow rate heat capacity value multiplied by the temperature of your hot stream going in minus the temperature of your cold stream going in. Once again, that's your greatest temperature difference, offering you the greatest amount of heat transfer. So again, this value in this denominator here is going to be your max heat transfer. Now relating this back to NTU, NTU stands for your net transfer units. And this is related to your overall effectiveness or your efficiency and your overall heat transfer coefficient U. So NTU is equal to our overall heat transfer coefficient multiplied by the area multiplied by that minimum mass flow rate heat capacity. Now, usually when you're thinking about sizing heat exchangers and looking at the data of them, what you're going to know about your process and your heat exchanger is going to be this information here usually. So your overall heat transfer coefficient and your designated cross-sectional area. And then these values here are ones that you can calculate along with your effectiveness or your efficiency. And so what you can do is actually use this to kind of give you a baseline to tell you how much heat transfer is possible for your heat exchanger. And so where our ratio comes into play is that this NTU, our net transfer units, can be related to a function of our efficiency or your effectiveness of your heat exchanger and this minimum mass flow rate heat capacity and your maximum mass flow rate heat capacity. And so this comes into play a lot when you're trying to size your heat exchanger based on your process. So this would deal with your different process parameters that you need to follow, what sort of expectations you want from your heat exchanger. This is very useful for that. A lot of times in chemical engineering, this comes up, especially if you go into more of the process side of things. You're going to be working a lot with sizing heat exchangers to perform. You want them to perform as efficient as possible, but also following your project parameters and what your expected output is. And so that is homework 5, part C, where we learned a lot about heat exchangers and their purpose and co-current and counter-current heat exchangers and what that difference is.